Hey guys, here we are in chapter 2, and we're looking at section 2.1, rational numbers on the number line. Our vocabulary is extensive, right? A lot of words, but the fact of the matter is you've seen most of these words before. So we're going to get right down to it. Natural numbers, when I think about natural numbers, I'm thinking about the set of numbers that starts with 1 and continues on forever, right? Notice there's no fractions or decimals in this. Notice we just start off with 1 and we keep going. Sometimes I call them kindergarten numbers or preschool numbers because generally you start off in preschool thinking, yeah, 1, 2, 3, you start counting that way. But then you get to kindergarten or first grade and somebody tells you about the number 0. Zero's a number as well, right? And so the set of whole numbers includes 0. So natural numbers are kind of like counting numbers. Whole numbers are like counting numbers with the inclusion of the concept of 0, of having nothing, right? And then integers would be the set of negative and positive whole numbers. So we might think of a set that looks something like this. Sometimes I talk about integers as number line numbers. If you ever observed a number line in a classroom situation, what you would see is that you have all of these nice whole numbers, negative and positive. So negative and positive whole numbers. Notice that natural numbers, whole numbers, integers were kind of growing in a sense as we go down that list. And so now we talk about positive numbers, and I know you guys know what those are. So I'm just going to highlight it in our integers. So positive numbers are numbers that are not negative, right? They're positive. And then we've got negative numbers, which are going to be these guys back here, okay? 0 is neither positive nor negative. Sometimes people like to kind of call it both, but it really isn't. It's neither positive nor negative. Rational numbers. A rational number is any number that can be written as a fraction, all right? So every number you can think of pretty much can be written as a fraction, sort of. So if I had the number 100, right, I can write that as a fraction of 100 over 1. So rational numbers, actually you see this word in here, ratio? Rational numbers are numbers that can be written as a ratio of any two integers. So anytime you have a number that can be written as a ratio or some kind of fraction of two integers, you got yourself a rational number. And like pretty much so many numbers that we work with find themselves in this category of rational numbers. So 1/2, -3 over 2, 9/12. I don't know, I'm just trying to think of numbers. 0.321 happens to be a rational number because I can write it as 321 over 1,000, right? Fraction action. So these are all rational numbers, numbers that we're totally used to. Infinity. Infinity is not a number. It's kind of like an idea because it's the idea that we can continue on forever and ever. And so infinity, we use this symbol that looks like an 8 laying down to rest. And this symbol basically means going on and on forever. And it means, I don't know, I almost want to say the biggest number you could possibly think of, but it's kind of the fact that there is no biggest number. So infinity means just going on forever and ever and ever and ever in terms of numbers. All right, graph. Oftentimes you will see, as I talked about before, integers are number line numbers, right? And so oftentimes we can graph the location of numbers. Well, we can graph the location of any rational number on a number line. Also irrational numbers too. Real quick, do you know what an irrational number is? Can you think of one? Huh? Somebody might be thinking pi because pi is usually the answer to something. And then somebody's thinking, well, pi is equal to 22 over 7, right? And so you're right that pi is irrational, but we're wrong because 22 over 7 does not equal pi. So this is not some kind of ratio that represents pi. It's an approximation. So if you ever saw an equal sign between pi and 22 over 7, it should be a wavy equal sign, which means sort of, kind of, approximately. All right, just a little fun for you. Back to the graph. So a graph, we can graph any number we want. We can place a number on a graph. We can even place pi on a graph. where would I do it, right? So 1, 2, 1, 2, 3, 4. Pi would be somewhere between 3 and 4. And we know that pi is approximately like what, 3.14 something something. I know somebody out there is like, I memorized it to the number 5,000th place. I see you, but I'm not dealing with you right now. So it's going to be right about here. So that's where pi would be. So a graph is a way that we represent the relationship between numbers being greater than or smaller than other numbers. Coordinate, if I were to talk about this place right here, if I would say A is at the coordinate of A is 1 on this number line, and sometimes we'll talk about XY axis pretty soon, and we'll discuss, we won't have one coordinate, we'd have two coordinates, right? So if I wanted to talk about this location, it would be 2 and 1, something like that, all right? So coordinate is a location on a graph, and then absolute value. I'm getting a little crowded here, but the concept of absolute value just means distance from 0. So here's 0, here's the number -3. If I say, hey, what's the absolute value of -3, which is what these two lines represent, or they indicate. If I ask you the absolute value of -3, the answer is 3, because the distance from 0 is just 3 steps away. Think about it in terms of if you were going somewhere, you wouldn't necessarily tell somebody that you were going 3 miles, -3 miles or +3 miles, depending on the direction. You might just say, I'm going to be about 3 miles from my house to do whatever activity. I don't know what I'm talking about, but you know what I'm talking about, right, kids? All right, good. So let's look at this one. First example, identifying coordinates on a number line. Name the coordinates of the points and graph each on a number line. Okay, I totally lied there. I did not read that. Let's try it again. Name the coordinates of the points graphed on each number line. Better. So this is not really hard. So the name of this point is -4, and this one's -3. You guys see where this is going? -2 is graphed on the number line 1 and 2. And then on this next one, we've got 1 and 1.5 or 1.5, 2, 2.5, and 3. So those are the ones that are graphed. However, we need to be aware of some symbols that are happening here. So when I look down here, I see that this arrow is highlighted. So that's an indication that I should continue. So I'm going to continue. So the numbers that I'm looking at are 1, 1.5, 2, 2.5. And since I'm continuing in that way, I can assume that 3 and then 3.5 and then 4. That was a little tricky, but we're pretty cool. So this is what we have to recognize that this is representing. And then here I would write this, the set of -4, -3, -2, 1, and 2 is the set that's being referred to here. Not too difficult. Over here, we're going to graph the numbers on a number line. And so let me draw my number lines for you. Okay, there we go. And then the next thing I want to do is observe what they're saying. So it looks like this particular one, part A, is continuing on. That we have this ellipse, which means on and on and on. In this case, to -infinity. We're going to keep going forever. And we look at the pattern and we see that we're going up by even numbers, but we're actually stopping or starting, if you want to think of it that way, at 6. So I'm going to plop my 6 down here. I'm going to plop my 4 down. I'm going to plop a 2 and keep it moving. I'm going to absolutely indicate what I'm doing here. And then -2. And then how do I indicate that I'm going to continue going on in this way? Do you guys remember from the last example? This is not something that I really do a lot of, but yeah, you would darken this arrow to say keep it going this way. Whereas notice that that's not happening here, so that lets me know that 6 is the end point or the beginning point, depending on how you're looking at it. All right, let's take a look at this example here. So we have a finite number of numbers here, only 4 numbers, so I only got to put 4 numbers on my number line. But notice we have this fraction of thirds, like everything is in thirds. So I split my number line up into thirds. So I've got my whole numbers here, my integers, 1, 2, 3, 4, -1, -2. but each space is split up into 3 equivalent spots, or at least or spaces, which was my attempt, even though it doesn't look really even. Bear with me. Okay, so negative 4/3 would be 1, 2, 3, 4, like literally 4/3 away from 0 in the negative spot. And then negative 1/3 is here, positive 2/3 right here, and positive 5/3 would be right here. And so we did it. So we're good. That's all we need to do. All right, integers less than negative 3 or greater than or equal to 5. All right, so we know that negative 3 integers less than negative 3. So we need to indicate that we are counting our integers, negative 3, negative 2, negative 1, and then or greater than or equal to 5. So I have all of these integers here that I'm not going to indicate. Negative 2, negative 1, 0, 1, 2, 3, 4, 5, 6, 7. So let me write those down. 1, 2, 3, 4, 5, 6, 7. And I'm going to put dots here like that. And then I'm going to shade in like this. And I'm going to shade in like this to imply that I'm going to continue in either direction. So when I made this handy template for the lesson, I didn't take out the answer, so I'm just going to talk about it because it's not that deep. Find each absolute value. The absolute value of negative 7. So negative 7 is 7 units from 0, therefore absolute value of negative 7 is 7. And then similarly, 7/9. 7/9 is 7/9 units from 0, therefore the answer is 7/9. Not really that deep. Sometimes people look at the absolute value bars as the positive maker, and I get it. It's not the worst way to think of it, though that's not exactly what it means. But yeah, every time you have the absolute value of something, the ultimate answer has to be positive, or 0, which is neither positive or negative. But you get what I'm saying. Okay, so we've reached our final example, which is to express the exact absolute value. But what we're going to do really is substitute in using the absolute value. And so absolute value symbol. So the absolute value symbol, I want you to think about it as parentheses with the power to make everything kind of positive, or the power to think of it as positive once you've done the operation. That's important. Somebody didn't listen to what I just said, and at some point in time, it's going to come back and get you. So I'm going to say it one more time. You have to do what's inside of the absolute value symbol first, then you make it positive. So 15 minus the absolute value of x plus 4 when x is equal to 8 tells me that I can replace x with 8. And now I need to do everything that's here. 8 plus 4, which is 12, the absolute value of 12, which we know to be 12. So this becomes 15 minus 12, which is 3. And that's my final answer. And that's really it. I'm going to just do a real quick example. What if this were 15 minus, I don't know, x minus 3? What I want you not to do is look at this and say, ooh, absolute value is the positive maker. I shall therefore make this minus 3 a plus 3. Not so fast. Remember, we're going to treat it like parentheses. Do what's in the parentheses, then make it positive. So here, 15 minus x minus 3. Now, this is not the problem. I just made this up out of thin air. But I'm going to throw the 8 minus 3 here. 8 minus 3 is 5. Now I will make whatever that answer is positive. You with me? I hope you are. And so positive 5 is, I'm sorry, the absolute value of positive 5 is 5, and therefore 15 minus 5 is what we get, which is 10. All right, babies, I hope you guys are feeling all right and comfortable with the information. I don't think that this was that deep, though I didn't mean to overtalk this video. You know, old people. Listen, let me know if you have any questions, concerns, or setbacks. I look forward to seeing you and talking to you soon. Take care.